uh, last time we reviewed the Thomson scattering. Particularly, we saw the properties of the properties in terms of how Thomson scattering scatters radiation depending on the direction. We saw the regime, the energetic regime, so the energy of the photon has to be negligible with respect to the rest energy of the electron. In particular, we saw that the capability of Thomson scattering of polarize radiation, which is initially unpolarized. And we saw also that the way it works. And so now let's move on with our review of radiative processes. This is very important in many contexts, which is the Bremsstrahlung. Bremsstrahlung, as you can hear, as you can see, is clearly a German word, which literally means breaking radiation, where breaking, if you look at the way it is written, you know that to break in English has two different meanings. Well, the pronunciation is the same, the writing is different. To break, B-R-A-K-E, the verb, the infinite verb, is the synonym is to slow down, to decelerate, which is exactly this case. Not to be confused with to break, the pronunciation is the same, B-R-E-A-K, which means to tear apart, to smash, to crack. So the pronunciation is the same, the meaning is different. So to bremsen in German is to break in this sense, so to slow down. Strahlung is radiation, so breaking radiation. Why? Well, the picture clearly speaks by itself. You have an atom, and at some point, a free electron. You see an electron which is just traveling and pass by the close to the nucleus of this atom, and because of the Coulomb force, of course, it is deflected. So deflected means it is accelerated. But you know by now that a charged particle which is being accelerated emits radiation. So that's exactly the Bremsstrahlung radiation. So radiation due to a slowing down. So the electron loses an amount of energy due to the fact that it is Coulomb accelerated by the passage, by the close by passage of in the nearby of an atom. This is also called in the atomic physics parlance. This is also called or referred to as free emission. Free refers to the state of the electron. It is free before the encounter. It is free after. So in any case, it's not a bound electron, either both before and after. So free. It's a transition from a free state to a free state, if you want. So as I said, from the point of view of atomic physics. So depending on the context, on the kind of textbooks that you use, particularly in the US, you might hear more preferably free emissions rather than Bremsstrahlung. Depends. In Germany, surely you will hear about Bremsstrahlung. So our goal now is to find out the total amount of energy emitted, depending on the different quantities that we will see, but also the spectrum. So how energy depends on frequency. In particular, what's the typical astrophysical context for this kind of emission? Well, if you need free electrons and ions, of course, you need a plasma, and particularly a relatively hot plasma. Otherwise, there's no ionized atoms. And we will see that it depends the more dense, we will see that in a moment, the more dense the plasma and the higher the contribution of Bremsstrahlung. So you have a lot of just electrons that are continuously accelerated just by passing close to the different ions. And as a matter of fact, in such contexts, you also have, in addition to the continuum spectrum, so energy distributed per unit frequency in a continuous way due to the Bremsstrahlung, and we will see how the mathematical dependence. In addition to that, you also see some lines, transition lines, because the plasma is so hot that you have some transitions between different levels. And so corresponding to these transitions, you also see lines superposed to the continuum due to the Bremsstrahlung. We will see a few examples of that. So let's try to figure out exactly the spectrum, as I said. If your aim is to derive things in a fully self-consistent way, you have to go through a quantum mechanical approach, which is not what we do now. We will see the kind of approximation that we assume, and then we will see how to correct for that when we account for the quantum mechanical corrections. So let's assume this is a trajectory of the electron, and let's assume that the deviation due to the attraction of the ion is relatively small. So we will treat the deviation of the electron from the straight line as a small perturbation, okay? And in particular, we call B the impact parameter, which is the minimum distance reached by the electron during its motion from the ion, okay? It's called impact parameter. So the idea is to exploit what we've seen, if you remember, when we dealt with the dipole approximation, we derived the spectrum. So the dependence of the spectrum, in particular on the frequency and on the Fourier transform of the dipole moment. So the idea is just to exploit that. So the goal is here to derive the dipole moment of the system. In particular, here we take as origin the position of the ion. So by taking that as origin, of course, the dipole moment is just E times the position of the electron. Here minus stands for, just accounts for the sign of the electron's charge. So E is a positive quantity, so minus E is just the charge of the electron. So if you work out the double time derivative of the dipole moment, you see you have V dot, where V is just the velocity of the electron. So it's acceleration. Just let's move from the time domain to the frequency domain. So it's just a matter of working out the Fourier transform of both sides of these equations. So you know by now that the Fourier transform of the double time derivative is just minus omega squared d tilde, where d tilde is just the Fourier transform of the dipole moment. And here is just the definition of Fourier transform of a function of, in general, of course, V dot is a function of time. From minus infinity to plus infinity. Minus infinity is when it is far away before the encounter, plus infinity when it is past the encounter. We also define a typical time scale. You see, in this encounter, you have just one single length, which is B, impact parameter. So you define the typical the velocity of the electron. So B over V is the only possible time scale that you have. This is called collision time. Now, we cannot work out this integral exactly, but we work it out in two different regimes. So in particular, depending on frequency, when the frequency is so small, such that omega tau is much smaller than 1, in that case, well, if you look at that integral, it means that, well, I didn't say that, but tau is the time scale over which V varies appreciably. So if you consider time intervals which are much shorter than tau, V can be considered as constant. If you consider time intervals instead, which are much longer than tau, V, or comparable or much longer than tau, V can change significantly, okay? So tau gives you a time scale with respect to which V can be considered roughly constant or variable. Now, let's see this integral in these two regimes. When, as I said, when omega tau is much smaller than 1, it means that V dot varies within a time interval in which the exponential term can be considered as constant, particularly as 0. Okay, so integral of V dot is just V calculated between the two extremes. So V at plus infinity minus V at minus infinity. So what you call overall, it's the overall resulting variation in the velocity. So delta V, just like that. This is the case, as I said, as omega. So you are taking a sufficiently low frequency, omega, such that omega tau is much smaller than 1. In the opposite case, when omega is large enough to make its product with tau much larger than 1, well, again, look at the time scale over which V dot varies. V dot varies over a time scale in which this guy instead goes up and down continuously. In particular, during an oscillation of this term, V dot has remained essentially constant, because V dot varies over time scales which are much longer than the time it takes for omega t to make a cycle. So it means that this kind of object just oscillating up and down, multiplied by something which is rather constant, it means that everything just cancels out. So it is 0. Of course, this is an asymptotic behavior, okay? So you have to take it asymptotically. Nothing can be said in the middle, but you can guess that there must be something in between, in the middle. But for the time being, we care just about these two extreme cases. So moving on, you see, just looking at this formula here, what we have to do now, what we have to find is just delta V. Delta V, you see, for obvious reasons, delta V in this kind of approximation, so when the deviation is small, is something which is perpendicular to the straight line, because of symmetry, if you want. If you decompose the Coulomb force acting on the electron on the parallel and perpendicular component, you see that the effect of the parallel component just cancels out, because when it is on this side and when it is on the other side, the parallel component changes sign. So the net effect, if you think of the impulse theorem, the change in the linear momentum of the electron due to the parallel component of the Coulomb force just cancels out. Instead, the perpendicular one acts all the time in the same direction. So the net effect is merely due to the perpendicular component of the Coulomb force, which is all the time acting, is attracting the electron towards downward in this figure. Okay? So it means that applying the impulse theorem, it means that the change in the linear momentum of the electron is just the corresponding component, so F, the Coulomb force, perpendicular component, just integrated over time. Impulse theorem. But let's work out this component. This is nothing but the Coulomb force. So if we call T0 the time at which the electron is at its closest approach to the ion, so when T is equals 0, the electron is right here, okay, here. So it means that minus infinity is here, plus infinity is on the other side. So you immediately guess when the electron lies here, we have this triangle. In particular, this side is just Vt. This is B. So just Pythagoras theorem. Z, E is the charge of the ion. Z is the atomic number. So Ze times E is the product of the two charges over square distance. Square distance from Pythagoras theorem is just this squared plus this squared, okay? This is mind that this guy is the magnitude of the force. We need to take the perpendicular component. Perpendicular component, if you call this alpha, I didn't write it, but if you call alpha this angle, the perpendicular component is just the cosine of alpha, okay? So B over R. But B over R is just B over, again, the side here is just the same here, square root, of course. So this extra factor just is a projection, is the cosine of this angle, just like that. So just, you see that this can be written as this way. So the denominator to the 3/2 power. And here is just a matter of calculating this integral. It's very easy. In particular, you can collect, for example, well, you take out of the integral z e squared b, well, over m, because you just calculate delta v. And then, for example, you take out of the denominator b to the second here, which to 3/2 means 1/b cubed. And then you multiply and divide by v over b to make a variable change here. So you multiply inside here v over b, and then you have to divide by v or multiply by b over v, just like that. So you are left with the integral, which is vt over b is just an adimensional quantity. You can call it x. So this is just a number. And I let you have the pleasure to calculate the result. This is just a calculus exercise. If you work out, so by calling this guy I, this integral I, this is a number. And if you work out the substitution x equal tangent y, you immediately see that x equal tangent y means that going from minus infinity to plus infinity, the integral turns from minus p over 2 to plus p over 2. The x is just the y over, the derivative of tangent is 1 over cos squared. And then, of course, this guy is nothing but. So very simple, and this integral is just 2. So pretty easy result. So replacing into the formula of the velocity variation delta v is just 2. You see, you start seeing you start appreciating the dependence of this velocity change. It scales with the square root of the electric charge, proportional to the atomic number, and inversely proportional to the mass of the electron, the velocity, and the impact parameter. So going back to now, we want to make use of the result that we obtained when we were talking about dipole approximation. So if you get back to that class, to that lecture, you see that what we ended up with was energy per unit frequency, 8 pi over 3 omega 4 over c cubed modulo squared of delta of d tilde. But d tilde is what we got in the previous slide. So in the two opposite regimes. So depending on the strength of the how big is the term omega tau. So just by replacing, now what we have to do is just replacing the value of delta v into this. There is a bit of calculation, but I think it's useful to see at least once in your lifetime this. So here I just copied the previous formula. So the power per unit angular frequency is all this guy in the regime of very small frequency, and 0, of course, in the other way. We obtain that delta v is just this guy. So replacing into that, there is a lot of coefficients here. It's a little bit complicated. It's easy to just get lost because there are many terms, but it's not conceptually difficult, okay? So just by replacing delta v into this, you see, first of all, you notice that you have a dependence on the atomic number squared of the ion, e to the 6. In particular, in the denominator, you have 1 over m squared, v squared, b squared. This is important. Here is just a sketch of what's going on. So the electron, being deviated from its straight trajectory, emits a photon. Here, do not pay too much attention to the direction of the photon. That's not the point. If you think carefully, you notice that the acceleration felt by the electron just is directed towards the ion. So if you remember that the sine square theta pattern, you see that the most likely direction is perpendicular to the acceleration, so is this way. But it can emit photons everywhere. But the more likely direction is, of course, this one here, perpendicular to the acceleration. So do not give too much, just forget about the direction. The concept is that the acceleration makes the electron emit photons. Bremsstrahlung. Okay, so this is just a reminder. The collision time is just the impact parameter over the velocity of the electron. You see, now we make a slight change. Here we look at the spectrum, this function is the spectrum, rather than as a function of frequency, as a function of the impact parameter. So, if you remember, tau by definition is B over V. So, for example, let's consider the first regime, omega tau much smaller than 1, omega B over V. So if you now express the condition on B, it becomes B much smaller than V over omega. It's a different point of view. You now imagine you fix the frequency and you wonder, you look at it as a function of the impact parameter. So you see that when the impact parameter is sufficiently small for a given frequency and a given velocity, of course, of the electron, you have this power. When the impact parameter is too large, you have nothing. Now, so far we calculated the energy emitted by one single electron with a velocity v with an impact parameter b with interacting with just one single ion. Now let's try to generalize things. In particular, we keep considering just one single ion, but we now consider a population of electrons. In particular, all of them having the same velocity. The only thing that we allow to change is the impact parameter. Okay, so we want to put together the contribution of all these electrons sharing the same velocity, having different impact parameters. To calculate this figure helps us. It's quite helpful because why? We consider the red ball here is the ion. Okay, so we want to evaluate in a time interval dt how many electrons come into play having an impact parameter between B and B plus dB. So what we have to do is just to work out the volume between these two cylinders, okay? So the volume of this region, which I showed as blue arrows, the blue arrows are the electrons which are moving, okay? They have all the same velocity. So all these electrons that I showed here in this picture have an impact parameter between B and B plus dB. So let's work out the number of electrons coming into play. Well, the height of this cylinder is just, if you consider a time interval dt, well, the electron that enter this cylinder is just v dt, just like that. So every dt, a number of electrons that are within the volume given by the area of this region here. And if you look at that, the area of the base, essentially of this volume here, is just 2 pi b dB, just like that, times the height of this volume, which is v dt. And so among brackets, here is the volume, but I want the number of electrons. So by small ne is the number density of electrons. So how many electrons per unit volume? So the number density of electrons times the volume, I have the number of electrons that come into this cylinder and interact with a given ion, okay? Now, let's consider not just one single ion, all the ions that I have per unit volume. But here, So let's consider a given volume dV. If I call Ni the number density now of the ions, well, the number d capital Ni, the total number of ions that are within the volume dV, is just number density times volume. Now, the total contribution that I have is what? Well, is here among the integral, if you look, is the contribution of all the electrons that are interacting with one single ion. Why? Because dV over d omega is the power of one single electron with one single ion times the number of electrons that are interacting with that ion, which is exactly the d capital Ne among brackets. By integrating between two extreme in terms of impact parameter, there will be a B minimum and a B maximum. We will see what they are. So all this integral accounts for all the power emitted by all the electrons within that are interacting, of course, within a time interval dt, with a given ion times the number of ions, which is an IdV. So by rearranging the position of the different infinitesimal quantities, so you can define the energy emitted per frequency interval, per unit volume, per unit time. And if you look at this integral, there's a lot of constant quantities. Let's suppose that the number density of both ions and electrons is constant. So this is something, all of this stuff can be just taken out of the integral. You just, in particular also the velocity, we've been considering electrons having the same velocity, I remind you. And so you are left with this integral. Of course, the energy we obtained above depends on the impact parameter, so you cannot take it out of the integral. And let's see, in particular, now it's a matter of replacing this rather complicated function into this integral. Of course, we have to keep memory of the two regimes. So here I copied what I've come up with in the last slide. So this is the integral I'm supposed to calculate, and this is the function that I have to put into this. So if you do that, well, first of all, let's settle all the coefficients. You see, here you have z squared. Here it is. You have another important quantity, is the product of the two number densities. Then you have e to the 6. Well, I let you check the correctness of the numerical coefficients. Let's focus on the physical quantities which are relevant. In particular, you see that m squared in the denominator remains. You have here v times v over v squared, so you're left with just 1 over v. And then the other is, I just commented. What about in the integral? Well, in the integral it's easy. You have b times 1 over b squared, so it's just integral of db over b, which you know very well. This is just the natural logarithm between b min and b max. We will see that in a moment. But before looking into the values of these two extremal values for the impact parameter, we immediately see that since they belong to the argument of they show up in the as argument of the logarithm, the dependence of the spectrum on them is quite attenuated. It's not so strong. If you double something that is, or just multiply by a given factor, something which is in the integral is just by adding, works like adding something. So it's not so huge dependence. So that means that even if you don't know them exactly, that doesn't really upset the calculation. Well, B max, what is that? Well, that's exactly the value, the boundary, which makes this function going from a given value that we just exploited to 0. So when b is comparable, gets larger than v over omega, this integral just vanishes. So that is equivalent to take V over omega as maximum value for B. And that's pretty easy. For the minimum value, you have to make two different considerations because you have two different possibilities, two regimes. Let's see why. Well, the first regime, when the impact parameter is too small, the approximation that we assume at the beginning, that the change in the trajectory of the electron is negligible, normal holds. Because when B is rather small, of course, as you see, the delta V, the change in the velocity, can be large enough to be no more negligible with respect to the velocity itself. So in particular, this limit will no longer, so the assumption that we made will no longer hold as soon as the velocity change is comparable with the velocity itself. So to find out the condition, we just set the velocity change equal to the velocity itself. I put equal, I should have put comparable with. It's just a kind of general guess. So B min, if you obtain, you use the value for delta V that we obtain, you see that it's just this guy here. And if you work out more properly, there's the numerical coefficient is slightly different, and I'm not going to go into the details, it's not worth it. But instead of 2, you have 4 over pi. More or less is the same. The second possibility you have to account is that when you think you have an electron for which you know the linear momentum, but if you consider a very small impact parameter, it means that you think you are thinking of an elementary particle for which you know both the linear momentum and both the position with great accuracy. There is a limit, which is given by Heisenberg principle. In particular, for a given particle with a given momentum, mv, you cannot have the position with an uncertainty which is smaller than h bar over the momentum. So you cannot consider an impact parameter which is intrinsically smaller than the limit set by Heisenberg's principle, by the uncertainty principle. So in that case, if you work out B min is just h bar over the linear momentum of the electron. So you have to make sure that both limits, both minimum value for B's are satisfied. You cannot violate either. So what am I supposed to choose? Well, here just put the same formula, just putting aside the two possible values for B min. So how can I choose them? Which is the one I have to take? Well, it depends. You have to take the larger one, because by taking the larger, automatically none of them are violated. And how can I know which is the larger? Well, you have to compare and to see. So let's work the ratio between the two. So if you work out B1 over B2, both min, so where B1 has a classical origin and B2 is a quantum mechanical origin, you see that you end up with this, apart from the numerical coefficient, let's focus, Z E squared over H bar V. If you multiply both numerator and denominator by C, you see that you end up with E squared over H bar C. This is the famous fine structure constant. This guy is the fine structure constant in the Gaussian system, of course. And so you know very well this is a number, pure number, which happens to be nearly 1 over 137. And beta because it's just V over C at the denominator. So it means that when B1 is much larger than B2, it means that you have to take B1. But this is the case whenever this guy is much larger than 1. But this guy much larger than 1 means that beta has to be much smaller than Z over. And this is indeed the classical limit. It means that the electron is non-relativistic, highly non-relativistic, I would say. So in the opposite case, when the other condition is fulfilled, of course, you have to take B2. So having in mind what B max and B means are, applying the recipe we've just come up with, this is the formula that we obtained that tells us the spectrum. So energy per unit time, per unit volume, per unit frequency. That's exactly what we want, what we wanted. In what case? Well, we are still considering a population of electrons sharing the same velocity. And we see the dependence on velocity, 1 over v. If you work out the calculations in full quantum mechanical treatment, so in quantum electrodynamics, you will see that there is a correction factor. To account for the correction factor, so for the correction that you need to apply to the classical formula to get the fully correct expression, you have to introduce a factor which is called Gaunt factor. And here I denoted with GFF as a function of V and omega. GFF, FF stands for free emission, okay? So it's just a reminder that this guy depends on the process. In this case, we are dealing with Bremsstrahlung, so free. So, and also it depends on both the velocity and the. It's a number. It's a number which is a function of both V and omega. And you see that automatically, if you compare the two, you see that as a consequence, this Gaunt factor is that accounts for the logarithm between the two quantities B max and B mean, and there's also some numerical coefficients. But apart from that, you see that the dependence is exactly, that's why it's very instructive to see the classical derivation, because you nailed, you guessed right, the dependence on the mass of the particle, in this case, the mass of the electron, its velocity, the number density of both electron and ions, as well as the atomic number, Z squared. Let's move on to a more realistic case. Why this is not really realistic? Because so far we considered a population of electrons having all the same velocity. This is pretty unrealistic, I would say. Thermobremsstrahlung, you add an adjective. What is the adjective? This adjective is describing the properties of the distribution, of the energy distribution of the electrons. So we no more consider a population of electrons sharing the same velocity. We allow them to have a distribution in velocity. Well, and what is the most natural distribution you can think of? Well, the Maxwellian distribution. So when you have a population of electrons in thermal equilibrium with a given temperature T, you know that the distribution function, which describes the distribution of the velocity, by velocity I mean the modulus, the magnitude, you know very well that this is the Maxwellian distribution. The Maxwellian, which is scales, has a dependence on velocity as v squared times the exponential minus v mv squared over 2 kt. Very important result. Here I wrote dne as the number of electrons having velocity between v and v plus dv, as this guy here. I don't care about the coefficients of the Maxwellian distribution. Of course, the coefficient has to make sure that the integral is normalized to the total number of electrons. I don't care for the time being. So now, let's figure out a population of electrons all having its own, all of them having their own velocities. If you were to know the resulting Bremsstrahlung, so each of them is emitting Bremsstrahlung, because you can think in just within a plasma, so each of them is just passing close to given ions. Well, you know the Bremsstrahlung emission for one single electron, it's just a matter of integrating the whole contributions. With some caveat, in particular, if you think that, as a matter of fact, an electron which is emitting radiation is emitting photons, but because of the discreteness of photons, of course, photon with frequency nu carry an amount of energy h nu. So it means that if you think of an electron with a given velocity v, its total kinetic energy is 1/2 mv squared. So it means that even in the extreme case that this electron is emitting all its kinetic energy into one single photon, the photon cannot have an arbitrarily large frequency. In the extreme case, the frequency of the only photon emitted by that electron is just that its energy equals just the total kinetic energy. So it means that for a given frequency, at a given frequency nu, only electrons with velocity greater than v min can contribute. If the electron is less energetic than the photon, there's no way for conservation of energy that it can emit that photon. So this is important to bear in mind. So now the total resulting thermal Bremsstrahlung, where thermal means you are thinking of a thermal population of electrons, is just the integral of the formula that we obtained in the previous slide for one single electron having velocity v, weighted by the number of electrons having velocity between v and v plus dv, which is indeed the term above, which is given by the Maxwellian distribution. Well, you have to normalize by the total number of electrons. The total number of electrons is the same integral, of course, integrated by, look, the boundaries of the above integral is between v min, for the very reason that I told you before, to plus infinity, of course. While in the denominator, you have to consider all the number of electrons. So you don't care. You have to take from 0 to plus infinity. If you work out this integral, here I just copied the formula that we obtained in the previous calculations. So it looks scary, but just because you have a lot of coefficients and constant. But I invite you to carry out this can be easily calculated. It's very easy. You see, here you have just the dependence on v. Here is 1 over v. So you have v squared, 1 over v, v times the exponential, just something for kids. Even kids can work out this integral. I encourage you to do that at least once in your lifetime. What you will see, you see that you have no more dependence on v because you integrate it in velocity. But you see that the variable which describes the property of the population is now temperature. So you are expected to see a dependence on temperature. And indeed, the result is this guy here, where I use different colors to highlight the important dependencies which are worth noting and that you are expected to remember. For example, to be very practical, during the exam I could ask you, how does, in the case of thermal emission, how does it depend, how the power depends on temperature, on ion density, on atomic number, and the most important one, on frequency. Because then when you measure radiation, typically you measure the spectrum. So you see clearly in a plot, for example, the dependence on frequency. So you have to know how thermal Bremsstrahlung, the behavior of thermal Bremsstrahlung is a function of frequency, if you want to be able to recognize whenever this is the case. So you see, the dependence on temperature is 1 over square root of t. So at a fixed frequency, if you increase temperature, the power decreases. This is just reminiscent of if you look at here, the formula here, you see that the dependence on velocity is 1 over v. But the average velocity squared, well, the quadratic average of the velocity for a Maxwellian distribution just scales as square root of t. So 1 over v just is reminiscent of that. And then you see, I don't want to comment again the number density of both ion and electrons as well as atomic number. The new guy is this guy here, blue. The dependence on frequency, you see, it's an exponential. Minus h nu over kt. It means that when h nu, when the energy of the photon becomes much larger than kt, this power drops. And this makes perfectly sense if you think. When you consider photons with energy much larger than kT. KT is the typical energy, the typical kinetic energy of the population of electrons. So if you want photons much more energetic than the typical kinetic energy of the electrons, well, of course, there are very few. How many few? How much few? How do you say? How few? Well, it depends. The Maxwellian distribution tells you. You see, you have, when you take extreme velocities, you have an exponential, negative exponential. So this is just reflects that. So you have a drop when photons have energies comparable with the typical kinetic energies of the population of electrons which generated them. And then the last factor is so-called velocity averaged Gaunt factor. I remind you, the original Gaunt factor depends on both velocity and omega. So you integrate it in V, so the dependence of omega just disappeared, but instead it gave the dependence on temperature, because this integral depends on temperature. So that's why velocity average, because it's the result of an average over velocity, and it gave the dependence on temperature instead of the velocity. So it's called velocity average Gaunt factor. It's also very useful to calculate you see a lot of constant, and it's also useful to calculate the numbers, just leaving the quantities meant to be in CGS unit, of course, or Gaussian, well, in this case are just mechanical units, mechanical and thermodynamic quantities. There's no electromagnetic, so CGS is the same. So it means that if you express temperature in Kelvin, these guys are number density, so centimeter cube, centimeter -3, and this is just a number. The result just here is just ergs per cubic centimeter per second per hertz. You will notice that instead of using this guy, I just put the emission coefficient. FF again stands for free emission. But if you look at this is energy per unit volume, per unit time, per unit frequency. So this indeed is the guy. I remind you, the emission coefficient is energy per unit volume, per unit time, per unit frequency, per unit steradian. So 4 pi is just reminiscent of that. I use this notation because, as I wrote here, if you take the textbook by Brad, which is one of the which I mostly use, you see that J, as used by Brad, is not meant to be defined by per unit solid angle. So there is some different assumptions in the literature. I adopted the definition given by Rybicki-Leitman textbook. Rybicki-Leitman says J, so the specific emission coefficient, is defined per unit volume, per unit time, per unit frequency, per unit solid angle. Brad just forgets about the solid angle. So if you take the Brad, you see this number, because this is meant to be already integrated. So that's why I wanted to keep this notation, to remind you that in our definition, J nu is also per unit solid angle. And given that this number just is already the result of integrating over the solid angle, this is just 4 pi J nu. So this is not to make sure that you are not confused when you just consult different textbooks and you see that with the same variable J nu, apparently there are different things that are meant to be, that are assumed to be described. So this is very useful also for calculations. And of course you have to know the Gaunt factor. In this case, you see that typically it's not so much different from 1. In particular, when you go to very low frequency, it can be in the range between 10 and 15. Here I put in the radio band, because the radio band, of course, is the band in which the frequency is relatively small. But you can have a lot of plots. For example, in this plot, the velocity average Gaunt factor is shown. So you see, it's just a few of several. 1, 2, 3, 4, 5. As a function of what? Of u. U is the energy of the photon over kT. So it's an adimensional quantity. So this is a semi-logarithm plot because u is given in logarithm scale, logarithmic scale. And here all these functions are for different values of a given parameter, which is called gamma squared. Nothing to do with Lorentz factor. Okay? It's just a parameter. This is in Gaussian units. So Z is the atomic number. Well, this is just a number. A temperature is in Kelvin. So depending on this gamma defined this way, you have different curves. But you see that it's 5, 4, 3. I mean, or it can be when you have very high frequency, then it can be smaller than 1, but it's a factor of a few in general. So this is an example of a spectrum due to thermal Bremsstrahlung. And in particular, you see, if you neglect the Gaunt factor, it means that you have to look at the dashed lines. So the dashed line is when you neglect completely the Gaunt, when you assume the Gaunt factor equal to 1. So you see, the dependence on frequency is only within the exponential. So as long as h nu is negligible with respect to kT, you have a constant function because there is no dependence on frequency. Only when h nu becomes sufficiently large, when it is large enough to become comparable with kT, then you start feeling the exponential drop. Okay, so in this very case, you see, what is the energy at which you see the drop? Well, it's given by kT. So in this case, in this example, I took the temperature as 50 million degrees. Well, if you think of a black body, for example, with 50 million degrees, it means that the energy, the average energy of photons is in the hard X-rays. So in terms of frequencies, 10 to 18, 10 to 19 hertz. And indeed, you see, it's pretty constant until you approach to the temperature. So you see the drop, the cutoff in the function due to the. So it's simply the interpretation is straightforward. When you move here, you are asking for photons which are supposed to be comparably energetic as the population of the electrons which are making them. So of course you are left with very few photons. But apart from that, you see that clearly this is a typical signature of a thermal Bremsstrahlung. Let me say optically thin thermal Bremsstrahlung. Because here I'm just showing you J nu. And if you remember from radiative transfer, the intensity, which is in the end what you measure, equals J times the size of the source only in the optically thin regime, when absorption can be neglected. So a constant function with an exponential drop at high frequency is just the spectrum of a optically thin thermal Bremsstrahlung. In particular here in this case, I took just as number density 10 to 6 particles per cubic meter, which is typical of astrophysical plasmas. I don't know if I told you, but in astrophysics, typical densities of gas plasmas is orders of magnitude less dense than what we have on Earth. On Earth, of course, you have something of 10 to orders of magnitude larger than this. And here, if you pay attention to the units of measure, here I put watts per cubic meter per hertz. It's just, okay, international system, but it's energy per unit volume per unit frequency. Here, this plot, I just took it from the Brad. So again, J nu in this case is just the spontaneous emission integrated over the solid angle. Now, we worked out the spectrum. What's about the total? If I don't care about the photon, I want to calculate the total energy, regardless of the frequency of the photons which are emitted. So what I am supposed to do is just to move from the specific quantity to the bolometric one. I am supposed just to carry out an integration over the frequency, And indeed, if you do that, so you end up with energy per unit volume, per unit time. So I remind you, this is the spectrum, so the dependence on frequency. If you work out the integral, again, this is something really for kids. What you see, and again, I highlighted the important dependencies worth to be remembered. So you see, pay attention. The dependence on number densities didn't change, as well as on the atomic number. What instead did change is the dependence on temperature. Before, the spectrum was t to the -1/2. Now t is proportional to the square root of t. It's no more inversely proportional to the. Before it was inversely proportional to the square root of t. Now it is directly proportional. So it means that the hotter, if you fix everything for a given plasma, so you fix number densities, what else? Number density, atomic number, you increase temperature, it means that the power, the bolometric power, so total energy per unit volume per unit time, will increase. And if you think that makes perfect sense, because hotter plasma means more energetic photons. So the corresponding accelerations, and so the power emitted will increase, the total power emitted. Mind that the Gaunt factor. Now the previously velocity average Gaunt factor depended on both temperature and frequency. Now you integrate it in frequency. So the result is something which depends just on temperature. And it is called frequency averaged value of the velocity averaged. So it's easier to write rather than saying. So it is denoted with just GB as a function of T, temperature. There's nothing more to add. And again, this Gaunt factor is again a number which is even easier to work with, because it ranges between, it's very close to 1, between 1 and 2, in particular between 1.1 and 1.2. And if you take 1.2, you have a 20% accuracy. Okay. So unless you need a very precise calculation, you can just take 1.2 and that's it. Much in the same way as I did before, I replaced all these constants to have a practical formula that you can use in real context. So again, for the very same reason, I'm not going to say it again. I just put here, this is just energy per unit volume per unit time. So here from the specific coefficient, emission coefficient, just the new subscript dropped, because now it's integrated over frequency. And this is energy per unit volume per unit time, just like that. So if you want intensity, J nu times, in the optical thing regime, times the size of the source, over 4 pi. That's why I wrote 4 pi. Now, what about absorption? And now, this is the very first, in our course, the very first applications of the beauties that we appreciated when we talked about radiative transfer. You see, you have a thermal populations of electrons. Thermal population. So you have matter in thermal equilibrium. So you know the source function. That's the Planck function. Now, for the specific process, we calculated the spontaneous emission coefficient. And so you automatically can calculate the absorption coefficient. Because if you want, you are exploiting Kirchhoff's law, because we are dealing with matter in thermal equilibrium. So surely the source function is B, is the Planck function. But you calculate it. And yes, the comment here I put is something that I already reminded you many times, which is, in this case, we can apply straightforward the Kirchhoff's law, because matter is in thermal equilibrium. If we had considered a population of electrons far from thermal equilibrium, we wouldn't know the source function. And to know that, you have to go back to a more fundamental level, and to derive Einstein coefficients. In this case, the task is easier. Thermal equilibrium, so we automatically know the source function. Kirchhoff's law. We know two of the three, and we know the third. The third is just alpha. Alpha free, yes, because we are considering the Bremsstrahlung process. Not only is that able to emit photons, but for the very same reason, when an electron can also absorb photons when it passes close to an ion, for the very same reason. Remember, when we reason in terms of radiative transfer and the fundamental level of when we spoke about Einstein coefficients, for the very same reason, the way nature works, the very same process can be responsible for both absorption and emission. So, okay, this is just a reminder of what the spontaneous emission formula is. So you just have to work out the ratio, just like that. It looks pretty scary, but it is not. It's just a lot of coefficients. But here you see, I wanted to highlight the dependence of the important quantities, in particular, the dependence of all these are here on temperature and on frequency on the side. Because the dependence on frequency, you can now reason. You can now make a few considerations. In particular, consider the two opposite regimes in frequency. Okay, this is just, again, I carried out the same exercise. I replaced all the constant, all the coefficients. And this is quite practical and gives you the result in, if you replace all the temperature and all the other quantities in Gaussian unit, you get the result in centimeter to -1, as expected for an absorption coefficient, of course. Let's consider the two possible regimes. So in the Rayleigh-Jeans regime, which means when at sufficiently low frequency, how much? Well, when the photon's energy is negligible with respect to kT, of course, this is the Rayleigh-Jeans regime. If you look at the frequency dependence of the absorption coefficient, you see this guy. Well, when this guy, you can Taylor expand, and you see that this one goes away, and there's h nu over kT, so you are left with a dependence of kT. You also have at the denominator square root of t, so t to the -3/2, and nu -2. And here you can make a lot of consideration, but I'll spare them because in a moment we will see a plot which is very meaningful. So, but see, first of all, that if you fix temperature and you change frequency, you see that the absorption increases when you move to lower frequencies. Instead, when you move to higher frequencies, absorption decreases. So if you think of a spectrum of a given source, it means that if you move to low enough frequency, alpha is sufficiently high, but a large absorption coefficient, it means that at some point the source will become optically thick. So when you move from low to high frequency, you move from an optically thick to an optically thin regime. So there will be a point at which you see that the change in the spectrum from the optically thick to optically thin. But optically thick, you know. Okay, I'll go on with the comments in the next slide. In the opposite regime, so when instead you consider the Wien regime, so when the energy of the photon is much larger than kT, you see, again, the negative exponential just fades away, so is negligible. So you are left with 1 over frequency cubed, so frequency to -3 and temperature to minus. So the qualitative dependence is the same. From a quantitative point of view, the dependence changes, but from a purely qualitative point of view, it is the same. So let's see now these two figures. I'm going to spend some time on them because they are very, very important. There are two examples, and this is a good test. I'm going to make several comments. if you understand all of them, because this is just a summary of everything that we've just seen about thermal Bremsstrahlung and all what you're supposed to know about radiative transfer. Let's focus on the top panel. Here you have three cases. I fixed the size of the source. So I took a source, these are typical values for astrophysical sources. So I took a source whose radius is just 10 to 15 centimeter. Could be, for example, the radius of a supernova. I took, well, the overall plasma is neutral, so I have the same amount of electrons as ions. So I took energy, the number density for both 10 to 10 particle per cubic centimeter. And the only variable that I change is temperature. So same region, same number densities. I consider three different Ks for three different temperatures. Now let's focus on the value at the central frequency here. You see, the red one is 10 to 5 Kelvin, 10 to 6, 10 to 7. So moving from red to black, you are increasing temperature. Now you see, if you remember the dependence on 1 over square root of temperature, you see that here you increase temperature and indeed intensity decreases, you see. But at the same time, you see something different. You see that the exponential cutoff, e to the minus h nu over kt, the higher the temperature and the correspondingly higher the frequency at which it drops, it cuts off. Indeed. But we also, oh, this is a log plot, by the way. And indeed, you see, in all of them, you have a constant function and then the dropout, then the exponential drop. Indeed, what we expect for thermal Bremsstrahlung. But you also see that in the regime in which, in the frequency interval, in which the function is more or less constant, it means that that's the optically thin regime. What you see in terms of I, in terms of intensity, is nothing but J nu, the spontaneous, times R, the size of the source. When you, so if you consider this guy here, let's focus on the black curve. If you now move to lower, gradually lower frequencies, if you remember the dependence of the absorption coefficient, as I commented before, the lower the frequency, the higher the absorption coefficient. So it means that the size of the source is always the same. So it means that tau, optical depth, which is alpha times R, increases when you move to lower frequencies. At the point at which you see it drops. The point at which you have this turnover, it means that this point here is when the optical depth becomes 1. Above is negligible, is much smaller than 1, optically thin. Here, optically thin. Then you move here, the optical depth becomes 1, and here much larger than 1. So in this regime here, you can no more speak of optically thin Bremsstrahlung. This is optically thick thermal Bremsstrahlung. And you see, if you pay attention, I remind you that in a log plot, power laws look like straight lines. So this is indeed a straight line. And if you can estimate the coefficient, the angular coefficient, you see that this is 2. This is no wonder, because you have a thermal matter emitting in optically thick regime. So this is the Rayleigh-Jeans regime. So you see, everything now makes sense. You see, so when you move, consider one given spectrum and you move along frequency, what changes is the absorption coefficients. But for a given size, you change the absorption coefficient, then it changes regime. You could move from an optically thin to an optically thick. And there's also something else. You see, if you compare the frequency at which you have this change from optically thick to optically thin as a function of frequency, you see that indeed, for example, let's consider here, this frequency here, 10 to 13 hertz here. When temperature is 10 to 7 Kelvin, here you are in optically thin regime. Now, if you decrease temperature, by decreasing temperature, what happens is that the absorption coefficient increases. But increases means that, of course, the optical depth increases. And here you are just turnover. And if you look the red curve with an even lower temperature, at that frequency here, you are fully optically thick. This is optically thick regime. Beautiful. You see everything which now makes sense. So if you are able to explain, to understand all the behavior from lower frequencies to larger frequencies, for all of them, and the behavior depending on different temperatures, it means that you understood everything about Thermalbrennstrahlen and its relation with and the aspect related to radiative transfer. So depending on the frequencies, you move from optically thick to optically thin regime. You see? And the last thing I didn't comment yet is if you work out instead the integral, so the bolometric intensity, which means you calculate the integral of all these functions, you will see this is a log-log plot, so you have to consider that. You will see that even if here the intensity at a given frequency is smaller for the hottest case, the integral is larger because the integral scales as square root of t. So overall, the overall power emitted by the hottest source is correspondingly larger. How much? Proportionally to the square root of temperature. So the integral indeed increases with increasing temperature. You see? Really beautiful. Now, if you are fully satisfied, fully happy with the first, let's see whether you can move on and also explain the bottom plot. In the bottom plot, what I did is, again, I kept the same size for the source, 10 to 15. Now I fixed temperature, in particular 10 to 7 Kelvin, so 10 million degrees, more or less the temperature you have within the center of the sun. Again, I consider a globally neutral plasma, so same value for electron and ion density. But now the density of this guy is something which I gradually increases or decreases. Let's consider I increase from 10 to 10 particles per cubic centimeter up to 10 to 18 per cubic centimeter. And the meaning of this plot is that here in the bottom you see the lowest density case, and in the top density is increasing upward. Okay. Now let's figure out what happens. If you now increase density, let's consider, okay, this case, the bottom function here, you have the same qualitative behavior I was commenting before. So this is the optically thick regime, and indeed you see the dependence is like proportional to nu square, the Rayleigh regime. Then here you have the optically thin regime, and then the drop, the exponential drop due to the exponential. Now, let's work out what happens when you increase density. Well, when you increase density, it means that absorption increases. Let's get back. You see, the absorption coefficient scales as proportionally to NE and I. So you increase that. But you know, what happens? It means that for a given frequency, by increasing density, you increase the optical depth, because you're increasing the absorption coefficient. So it means that at some point, by keeping increasing density, you move from an optically thin regime, you see, and here at this point, I'm in the optically thick regime. If you carry on doing this, at some point you see that the range of frequency for which the regime is optically thin just shrinks, gets smaller and smaller, narrower and narrower, at the point at which the optical depth will be much larger than 1 at any frequency. But if you think in terms of radiative transfer, in the end, when you just stuffed in so much gas that you made the source optically thick at any frequency, well, you have a thermal source in thermal equilibrium, which is optically thick at any regime. That's a black body. Because intensity, when they are optically thick at any frequency, it means that intensity equals the source function, optically thin regime. But the source function in the case of a thermal population is a black body, is a Planck function. So you see how the Bremsstrahlung tends to approaches the black body. And you immediately see that if you keep adding gas, keeping the same temperature, the spectrum won't change, will remain the same, the black body one. So you also appreciate the statement that I made when I was talking about radiative transfer. If you remember, I told you if you fix temperature and size of the source, the black body is the most efficient radiator. You cannot go beyond. If you fix temperature, you fix the size of the source, there's nothing that can radiate from that source more energy per unit time than a corresponding black body. And you immediately see this from here. Unless you call for a coherent process. Coherent process can just bypass all this stuff, but this is something different. So my advice is spend several minutes in your lifetime on this very couple of plots. Think all the possible, I can just take them during your exam. I take this plot or something alike, and I could just, if I see that you understand every single aspect of these two plots, I get convinced that you know everything about, in this case, thermal Bremsstrahlung and radiative transfer. Here there's just, it's like we've seen so far many different aspects. And it's like studying the single sheet for the music of just one single instrument. Now we see all the orchestra playing together. We see the orchestra, but you have to be able to recognize the individual sound of each instrument. You see the result, but you also see by now you should understand. So if you get into troubles, that's a good exercise to highlight, to find where your knowledge needs to be reinforced. Okay, so this is a very good test. If you can immediately explain what I just said, it means that you are in control of the most important things that have to be known. In addition, if you want, you have all the ingredients by now to reproduce these plots. I'm sure all of you have your own, I don't know if you are more familiar with Mathematica, with MATLAB or NuPlot, whatever program you use to plot functions. You should be able to reproduce this. If you can do that, it means that you understand everything. You have all the ingredients, you already have it. So you should be able to do something like that, or just even change, and just easy. So I strongly advise. If you remember, this is a slide that I already showed you when I was talking about radiative transfer. And I told you, oh, there's a lot of information here. We will meet this again, and we will be able to do a lot of to make a lot of points. That's exactly, you see, this is just the summary of what I just told you. Optically thick, optically thin. This is Bremsstrahlung, so constant until you get to the exponential drop-off, and as much as you keep everything fixed, and you increase density, you see that the optically thin regime just shrinks, and then finally the spectrum approaches the one of a black body. Beautiful. This is really beautiful. Just a few examples, a few astrophysical examples of what I'm talking about. Okay, this is just a qualitative example of, for example, of what I just told you. You see, tau here is the turnover frequency, is the frequency at which the corresponding optical depth changes from negligible with respect to 1 to much larger than 1. And indeed, this is Rayleigh Jeans regime, so it has to scale with nu squared. This is, for example, as I said, the case of a hot gas. Hot gas, you see, if you remember, the emission scales with the density of both ions and electrons. So it means that in order to have a good emitter of Bremsstrahlung radiation, you need hot gas, and particularly the density cannot be too small. Otherwise, you don't have enough gas, enough electrons to have a significant emission. So you can have a lot of examples here. Just put, for example, compact sources, compact regions in which you have star formation. So temperature of the gas is typically a few thousandths Kelvin. You have hydrogen, which is fully ionized. So a lot of protons and electrons free to emit, as I said. Or in my case, I'm in the field of more high energies, so X-rays. So if, for example, there are X-ray binaries, one of which is a compact source. So the gas, which is moving on an accretion disk around these sources, or just which is falling onto the surface of a neutron star, for example, can be hot as a few million degrees. So in that case, you have a region surrounding this X-ray binaries, which is filled up with hot ionized gas. Again, we see that. And you can measure the temperature because you measure the energy at which you see the exponential cutoff. Or yes, this is even a more extreme case. For example, if you ask Professor Rosati, he's studying particular clusters of the galaxies. And if you imagine, if you think of a cluster of galaxy as from the gravitational potential point of view, you realize that the gas that lies in the center of these clusters of galaxies lies in the well, in the very deep well of a gravitational potential. So it means that the gas that goes in has a huge kinetic energy. So again, you see how hot it can be 10 millions, 100 million degrees. So we are talking about gas which is really, really hot. So you would expect hot X-ray emission due to Bremsstrahlung. And indeed, that's what it is observed. And knowing the properties of Bremsstrahlung, you can also estimate the amount of gas by estimating the density. So you can learn, once you apply, you recognize that it is Bremsstrahlung emission from the center of these clusters of galaxies. You can estimate a lot of things, starting from the knowledge of the Bremsstrahlung emission process, by measuring the temperature, by measuring the density, just by the amount of energy that you receive in the X-rays. So there's a lot of physical quantities that you can estimate, going through the knowledge of Bremsstrahlung in this case. And this is the picture of what I just said. This is a famous cluster of galaxies in the Perseus constellation. This is just the optical image. This is the X-ray equivalent. So you see, I just told you this is a color-coded image. So it means that, of course, the brighter, the hotter. So the more intense the X-rays, and so the correspondingly hotter temperature. And yes, this is the energy spectrum of the same guy. So this, you see, energy is in keV. So indeed, these are X-rays. So you measure the exponential cutoff. So you measure the temperature, and as an independent piece of evidence that the temperature is really high, you also see some emission lines due to iron. And the emission lines, the energy of these emission lines is a few several keV. So in order to ionize those energy levels of ion, necessarily you need a temperature. You need gas which is that hot, otherwise you cannot ionize it. So the fact that in addition to that, you see also emission lines whose energy is of several keV, that's evidence, independent evidence that the gas is really that hot. Yes, this is another picture another figure that I have taken from the BRAT, in which you see, in this case, in the radio band, you see the turnover from the optically thin to optically thick gas emission, superposed to other kind of emission. There's a lot of things, as I said, that you can measure, physical quantities that you might be interested in. For example, let's suppose you have a resolved source. What is a resolved source? A source whose solid angle can be measured. So you know the solid angle subtended by the source to you. So I just took, you see, the spontaneous emission coefficient. Here I just call C1 the numerical coefficient that I put already. So I left the dependence on the atomic number, temperature. Here I just took, of course, a neutral plasma, so Ni equals Ne, so that's why Ne squared. And the rest is just the same, what you already know. Now, if you assume that the source is optically thin, and you can see from the spectrum where it is, in which frequency regime it is optically thin, well, it means from radiative transfer that intensity is just J integrated. I kept approximating J times the size of the source. If you want to be more precise, you should integrate the emission coefficient over the path across the source. So let's assume the source is a radius capital R. That's the intensity. That's what you measure, in the assumption of an optically thin, of course. Otherwise, you have to take into account the value of the optical depth, and you know very well from radiative transfer. So just by replacing the value of the spontaneous emission into that, you see that, assuming that the temperature is constant within the source, otherwise you cannot take temperature out of the integral, of course. But this is quite a reasonable assumption, depends on. Then the only quantity that you cannot that you have to express as an integral is the integral across the source of the density squared, the number density squared. In some cases, you can just, if you want, you can define the average of the squared density as times the radius of the source equals to this. This quantity is called, in the literature is called emission measure. It makes sense because it tells you how much gas, very broadly speaking, how much gas you have contributing to the emission, to the Bremsstrahlung emission. So, for example, if you measure the spectrum, you measure the frequency at which you see the exponential cutoff. That means you can measure the temperature. So temperature is something that you can measure. I is just, you are measuring the amount of energy your detector is measuring. So in order to do that, you have to measure flux density, but you have to divide by the solid angle subtended by the source. That's why this holds for result sources. So you can estimate, as I said, the emission measure. So depending on whether you know the size of the source or whether you know the density, you can estimate the other one. So this is really powerful. And this comes from the fact that for a given amount of gas, with a given temperature, with a given optical depth, regime, you know how much energy you are expected to measure. So when you measure the energy, you can estimate the remaining quantities, in this case, the emission measure. This comes from the knowledge of how much energy you expect from a given source emitting through Bremsstrahlung radiation. Or for example, this is another example concerning the specific luminosity. Well, again, let's suppose we have an optically thin source. So if you think of the definition of the specific of the spontaneous emission coefficient, energy per unit volume, per unit time, per unit frequency. So it means that if you want to integrate over the volume, just integrate 4 pi j nu in volume. And what you are left with is just energy per unit frequency per unit time. But energy per unit time is luminosity. Per unit frequency is the specific luminosity. That's indeed this guy. The integral here is over Vs, where Vs stands for the volume of the source. So just, again, using the formula we've come up with for the Bremsstrahlung, in the case of the emission coefficient, this is just this guy here. This is just something that we already know. So you can express, again, the specific luminosity as a function of this quantity. Assuming, again, under the same assumption of a constant temperature throughout the source. Again, in this case, you see that you have the integral of the square of the number density times in volume. In the previous case, it was a linear integral through the source. This is over the volume of the source. Again, in the literature, people might refer to this quantity as an emission measure. So there is some confusion about names, but the important is that you see what you have, and so you immediately see whether it is integrated over the entire volume or within the size of the source. So, and of course, when you integrate over frequency, you have the bolometric luminosity, or just luminosity. And so, by measuring the luminosity, by measuring temperature, you can immediately measure the density, if you know the volume, or the other way around. And this is an example of a paper which was published a few years ago, in which I was one of the co-authors. Beautiful. We saw, this is about a supernova, which at some point got really bright in the X-rays. So we measured the spectrum, how the X-ray spectrum changed as a function of time. And we realized at some point the brightening was due to the fact that the shock wave due to the supernova, if you want to know more about supernovae, just attend my course. This is advertisement. My course in motivation. But apart from that, let's imagine an explosion, and then you have a blast wave, which is propagating through the interstellar medium, to the medium surrounding the supernova. We found out that there was a shell surrounding the supernova, a thick shell, which we inferred was the result of a past emission of the supernova. The massive star, decades prior to the final explosion, just underwent a significant episode of mass loss. It emitted a shell of mass. This just expanded in the meanwhile. Afterwards, some decades afterward, just the final explosion, so blast wave. So at some point, the blast wave reached and crossed the shell. It shocked the shell. By shocking the shell, we will see when we will be studying shock waves, beautiful. We will see that the result is just, it heats up the shell itself. So the shell becomes really hot when the shock wave crosses the shell. So you have ionized, full shell of hydrogen, which becomes ionized, very hot. You start seeing a lot of Bremsstrahlung emission. So in detail, what we did, okay, this is just the luminosity I showed you before, the specific luminosity. So we took the spectrum, the X-ray spectrum, we saw the exponential cutoff, so we measured the temperature that at some given epoch, this was nearly 500 days after the explosion, was 20 keV, so very hot. We measured the luminosity, we measured how much energy we received in the X-ray. So we measured the emission measure in the sense that the average value of the ion density squared times the volume. But the volume is a shell, it's not a sphere, it's a shell. The volume of a shell is the radius of the shell times delta R. Delta R is the width of the shell. Well, we knew from the shock properties, I'm not going to spend too much time on it, it's quite tricky then, but we knew the delta R shell. So the width of the shell was 10 to 16 centimeter. We knew R because we knew the velocity of the shock. So we knew the volume. We measured the density. Beautiful. And measuring the density, you know the volume, you know the density, you know the total amount of mass. So we could measure the mass that was expelled decades before. And we found that it was comparable to one solar mass. A lot of mass, a huge mass was expelled. And this is really, if you care about stellar evolution, particularly stellar evolution of massive stars, this is something, what happens in the very last decades, hundreds, centuries, 1,000 years before the final explosion. This is something very complicated. We know very little from theory, particularly, but now in the very last years, we began to learn more. Thanks also to this. You see, and here we made use of the knowledge of Bremsstrahlung. We recognized thermal Bremsstrahlung. We could measure density. We could measure the mass of the shell. So we learned a lot about how massive stars die, something which was not known, or partially. Of course, you don't learn just from one single object, but that was very important. And that's all for the thermal Bremsstrahlung. So I would say, so next class will be on Friday, remotely. I won't be here. Apart from that, the rest works just the same way. And we will begin a very broad topic, which is synchrotron radiation, which is hugely important in astrophysics, but not only in astrophysics. You know, a lot of just detectors just produce also in the lab synchrotron radiation. So knowing everything about synchrotron radiation is tremendously important. Any questions? Okay. So let me stop recording.